we're going to take a look at something called symmetry. We're going to look at symmetry. Now, I'm actually going to give you a little guided notes paper, so you don't necessarily have to take out a notebook. I'm going to give you a paper here. But we're going to end up, a lot of this topic is visual, and meaning that we're going to be using some type of graphing tool. For most of us, that's Desmos. So actually, if you do want to dig up something, that I really encourage you to have access to Desmos, whether it's your computer or your phone. And again, we're going to look at symmetry. Now, I expect that you have some exposure to symmetry. You've done it in, believe it or not, in some algebra classes. You would have done it a lot in geometry. It turns out that these graphs that we're looking at are very symmetrical. If you just think back to the time where you drew some of these on that crazy red paper, you might even feel like that some of the numbers that you got in your chart were like the same numbers. And when you start getting like the same numbers and you start graphing the same numbers, it's not a surprise that the shapes you get are symmetrical. This is called a lemniscate. I don't know if you were ready to have that roll off your tongue when you came to class today, but this is a lemniscate. It's a certain kind of graph that has two petals, and it's very symmetrical. If you think about it, I could draw a line, if you will, through the middle of this lemniscate, and that line would be known as 0 degrees. Now, 0 degrees cuts this lemniscate in half. And there's many ways to think about that. A lot of kids just kind of look at it and say, yes, it cuts it in half. I always like to think of it as folding. If you fold over the symmetry line, if you fold over it, it'll land right on top of itself. But it's equally true that this graph is symmetrical with another line. We could call that line 90 degrees. Make sure you realize that 90 degrees traverses the whole way through. So 90 degrees is all sides of it. But that line cuts the graph in half. And again, if I fold the graph, it'll fold right on top of itself. Again, pretty kind of basic stuff. But and this is kind of like the thing that's hard for people to see, but I want to try to teach it to you. If you can fold a graph over a horizontal and a vertical line, if you can fold it over both and say yes to that, that means that there's also something known as point symmetry. Point symmetry means a double fold. It means that I would fold the graph over a horizontal line and I would fold it over a vertical line, and it would still end up right on top of itself. So we have a point also as a third type of symmetry for this one. Okay, now that's just for a lemniscate that's shaped like that. What about some other graphs? Of course, that's what we want to look at. I have a little guided paper here. It'll serve as some notes. It'll also serve as some problems for you to practice in class, and maybe also, if you need to, a little bit as homework. Okay, now again, remember, a lot of this is visual. It's not like we're trying to memorize these answers, but I am trying to help you understand how to see them. All right, and again, as I tried to show you in that first problem, we have line symmetry, but we also have something called point symmetry. Let's just do a quick kind of review of that. And on purpose, I want to show you two examples that are not our types of graphs, that aren't just polar graphs, because I just want you to remember that it could be any kind of shape. And so if I'm going to have line symmetry that might be like a vertical line, if I'm going to have line symmetry that might be like a vertical line, then I would expect to see some type of graph maybe on this side, we'll say like on the right side, which would be then symmetrical with something that, not surprisingly, would be over here on the left side. And that is not a polar graph, but it is an example of a graph that is symmetrical with more like a vertical line. And just to have one more to look at, maybe one that's symmetrical with a horizontal line, maybe a horizontal line down here. And if that be the case, then I would expect to see, or I could see a graph up here. Maybe it's a graph that kind of looks like this. Okay, I'm just kind of making up a shape, but we would expect then to see a symmetrical shape down here. That's a little different looking, but that would be symmetrical with a horizontal line. Now, I did something here. Do you realize it? Sometimes we just kind of accept what the teacher did. Like, sounds good, Miss Naylor, but there's actually something else that's true about both of these. How about the one that I just drew? Who's to say that it's not also symmetrical with a vertical line? If you think about it, if I fold over that vertical line, it also would have symmetry. And that means that it has symmetry with a horizontal and a vertical line. And it's the same thing over here. If I fold this first one, if I actually fold it down, or if I say that I'm splitting the graph in half, it also could be a horizontal line. So here again, we have symmetry with a horizontal and a vertical. Now, this doesn't happen all the time, but I did want to share that when it does happen, when it's horizontal and vertical, that means we have point symmetry. And point symmetry is always when there's two lines of symmetry. Honestly, it's kind of the harder one for kids to see. Let's do an example of point symmetry with a different type of graph. Okay, let's say I'm symmetrical about this point, but my graph is the letter P for polar. Now again, it's kind of weird, but if I have a letter that is shaped that way, and I have point symmetry, that means that I should be able to take this letter and fold it down. When I say fold it down, what I'm really referring to is folding it over a horizontal line. Now what does it look like? Okay, well, it's been folded down. It's symmetrical. It's going to look something like this. I'm trying to basically draw an upside down P, but not make it quite look like a B. But I did fold it down, so we have our first line of symmetry. Okay, but then there has to be another line of symmetry. I would have to take this and also fold it over. And if I fold it over, that means I'm going to be folding it over a vertical line. Okay, so I end up with kind of like a twofold. And this time my P is going to be flipped and be over here. It's not supposed to be a D, but it's the symmetrical movement of that original P. Okay, so this P ultimately reflected over here. If I have both of those shapes, then I would have point symmetry. Let's look at this with some polar equations. Okay, this is what we're really trying to do. And here's what I'm hoping that you'll do. Type these in, check them out, and then let's talk about them. So we'll do this first one, 3 plus 8 cosine of theta. Actually, before you do type that whole thing in your computer, do you know what kind of shape that's going to be? I mean, do you recognize that formula? Just as some extra reminder, this is going to be a lemma. A lemma is always when you have that A plus B style. And lemma can have loops. They have a loop if the second number is bigger than the first number. Okay, so we're anticipating a lemma that has a loop of 5. Check it out. This is one way to get familiar with these. Can you guys see the Desmos up here? Okay, yeah, in settings, Remember, there's some things you want to change. You want to change it to the polar grid, and then you want to change it to degrees. Now, I'll tell you, the X and Y axis, it's kind of weird. The X and Y axis doesn't really exist, but it's still numbers on this setting. And a lot of times, -10 to 10 is just kind of a good starting point. And if you ever get like way zoomed out or way zoomed in, you can reset this to -10 to 10. Okay, and then degrees. We like to have it in degrees because that's typically how we think of angles. For some reason, my screen is, I want it to kind of be a little more square. Okay, so 3 plus 8 cosine of theta. How'd you do? Does it look like a Lima sign? Okay, it's got a loop. That loop is of size 5, as we kind of expected. Okay, but we're looking at this in a new way today, and that's really what you're doing. Just looking at it, you're trying to find a line of symmetry, or maybe a point of symmetry. Okay, now I find that a lot of kids say or can see this line right here. I want you to see that red line. It's definitely symmetrical. How do you describe that line, though? You don't want to say x-axis, because there is no x-axis technically. What you mean is either the polar axis. Now, the polar axis, remember, is the same as 0 degrees. So you could say the polar axis, or you could say 0 degrees. Okay, now when we say 0 degrees, we want to give that as an equation. And so let me make sure that I model this for you here, because it's as easy as just saying theta equals 0 degrees. That would actually be the equation form. And as I said, that's the same as the polar axis. Now, to be clear, you don't have to say both. You can. But I think as we look at that Lima sign, that's the only line that basically we can fold the graph over. And so it only has one line of symmetry. Let's look at the next one here, 6 cosine of theta. Okay. Yes, you're going to type it in, but just as one extra piece of discussion, do you know what shape that's going to be? Okay. Off the chart, that is going to be a circle. That's a circle because it basically has that coefficient, which represents the diameter. Again, the diameter is always that coefficient. So what does it look like? Are you seeing a circle with a diameter of 6? I made mine orange because, well, maybe it literally is an orange. Actually, it's just a circle with a diameter of 6. I want it to look more circular. There we go. Now, circles, they're pretty symmetrical. In fact, you might say they're the most symmetrical shape that exists. How do we describe that? Well, you should feel like in the middle is that point where it's symmetrical. You might say that it's perfectly symmetrical right in the middle. That's because right in the middle, you end up with a line of symmetry that's both horizontal and vertical. Okay, now that what we're trying to basically argue here is that there's a point of symmetry, and it's the middle of that circle. Now you can describe that point, because if the diameter is 6, that means that that point would have to be at 3. It would be at 3, 0. So we have a point of symmetry. Okay. Now, it's kind of hard to describe the vertical line in polar math. It's kind of hard to describe that vertical line using theta. So we basically say we're not going to, all right? But it's still there. And since we have a horizontal line and a vertical line, that means we have point symmetry, which is, I think, what we want to give as our good answer to this one. Now, when we say 3, 0, just in case you're wondering, we're not talking about x and y. Careful with this. We're talking about r and theta. You see, if I rotate 0 degrees and I count out 3 circles, then I would be at that point 3, 0. I know it looks the same as x and y, but technically it's r and theta. Okay, so we have a point symmetry. Let us proceed over to this next one where we have a 3 theta, specifically a 6 cosine of 3 theta. And remember, this is the only equation that is going to always produce a rose. This is the formula for a rose. And remember that the letter or the number that's beside theta, the number 3, in this case because it's odd, is going to give us 3 petals. So we're going to have a rose with 3 petals. Are you checking it out? It just sometimes helps for you to graph it yourself. And you should see a rose. It has 3 petals. Now, probably of everything we've talked about so far, it's been pretty easy. We get to the rose. I'm not saying it's hard, but there's a little more going on here. So try to soak this in the best you can. There are some lines of symmetry. Do you agree with me that this line, that once again is the polar axis? Now, if you fold over that line, you should feel like that this petal here on the right would fold down, but you should feel like this petal up here in the left corner would also fold down onto this petal in the bottom left corner. So if I fold this graph down, it definitely is going to be on top of itself. I want you to notice, though, that this line of symmetry is going through the petal. I also want you to notice that over here, the line of symmetry is between the other 2 petals. Now, I said something there that's pretty important, so let me say it again. The line goes through the petal. Over here, it's between the petals. So what's wrong with this line of symmetry? Well, nothing. You see, it does the same thing. This line of symmetry goes through the petal, but it's also between the other 2 petals. Okay? There's something happening here. By the way, this line of symmetry would be 120 degrees. 120 degrees. We will describe it that way. Again, I ask you, then what would be wrong with this line? Well, the answer is nothing, because it also goes through the petal and is between the petals. Now, it depends on how your brain is gifted. Some students have trouble seeing that if you fold this rose, that it still would fold. And maybe some of you don't have trouble seeing it. I can't take this and put it on paper for you, but if you think about folding it, you kind of fold it diagonally. And this petal right here, this petal would fold on top of this one. This petal right here would fold right on top of itself. So it does have that symmetry, even though it's diagonal. Okay, so we end up with 3 lines of symmetry. All 3 of those lines of symmetry count for this rose. Notice where they are. They're at 0, 60, and 120. They're at 0, 60, and 120. Okay, we want to be able to say that correctly. We want to be able to say theta equals 0, theta equals 60, and theta equals 120. Look at how I'm saying it. I'm just writing it as an equation. I am putting some commas just because it repeats. Now, sometimes students say, well, what about the other side? Well, remember, the other side is the same lines. So I don't need to say it again. I don't need to say the larger values. This is good enough. But there's something mathematical about these numbers. These numbers are all 60 degrees apart. In math, when you have numbers that follow a pattern like this, we can describe it with a formula that says that would say 60 times k represents that idea of being 60 degrees apart. The first number is typically added onto the end. And so we get a little formula that says 60k plus 0. Does that look like something from a few months ago? We did this when we talked about asymptotes. Now listen, the formula that I just wrote says that every angle is going to be 60 degrees apart. That's the 60k. And then the first one is at 0. Okay, it's just another way to be a little more exact. Let's do one more. 6 cosine of 4 theta. Now, I'm sure you're going to type this in, but maybe just think with me for a moment. This is still going to be a rose because it's got that 4 theta. And because 4 is even, remember, because it's even, we shouldn't be surprised to see 8 petals. 4 or 6 cosine of 4 theta. Okay, kind of neat. If there's anything that's kind of neat, you get this neat shape here. You get a rose. Lines of symmetry. Do you see them? They go through the petals. Once again, 0 degrees. It's been a pretty popular answer today. 0 degrees. How about okay, now again, you should be able to say, okay, Ms. Naylor, yes, it goes through that petal. We just want to say, yes, it goes through it. How do we describe it, though? We have to think about the size of that angle. Now, that angle, if you look at Desmos, we're just kind of looking at it. That angle is smack dab between 30 and 60. Okay, we should be familiar that that number would be 45. So you should see 45 degrees. Okay, there's a lot of lines of symmetry. They go through the petals. Now, what was the other thing that I said? Between the petals. If you're going to be between the petals, then you're looking at these lines. For example, between the petals. Oh, it's like a new line. Here's another one that's between the petals. Again, a new line. And the truth is, if we're going to put all of them down, between the petals would also encompass those lines of symmetry. Okay, now, when you have a rose, there's always symmetry through the petals and between the petals. And so we have a lot of lines now. Okay, I want to make sure you guys are able to determine, I tried to make it a little bold, but I want to make sure you can determine this line right here, and you have to understand that that is between 0 and 45. Okay, I'm on this bold one right here, between 0 and 45. It would just be a simple math computation. It's just half of 45, which is 22.5 degrees. It's the same thing for this next one that we'll kind of make bold. It is between 45 and 90. And the number that's between 45 and 90 is just another 22.5 degrees. So that would be at 67.5. Sometimes you have to do a little bit of thinking about some numbers that are between. Okay, let's write these down. This one does get a little bit overwhelming, but technically there's these many answers. We started at 0, and then we had that one that was between, that's at 22.5. We had a nice 45, and then we had another one that was between. Now that's just another 22.5, but another 22.5 is 67.5. And then we get up to 90. Now, a math student like you should not get super overwhelmed that we have so many answers, but rather that each of these numbers is really just another 22.5 degrees from the one before it. Okay, so there's a pattern to these numbers. I'm just adding 22.5. And yes, you end up at some of these decimals, but you also end up at some of these nice solid angles. But we have quite a list here, which means that we could write this as a formula. You see, the formula says that every number in this list is in a multiple of 22.5. So we could say 22.5K. You also want to add the first angle, but it's kind of nice because the first angle has, so far, it's been at 0. If you're saying, well, which answer do I put down? I want you to understand as part of today's lesson that all of these answers count. Technically, the little formula is the best answer because it's describing every number. But you could also list those numbers. There's one more symmetry. Is it another line? It is not another line. It's actually a point. It's actually a point. It's the point right in the middle. Now, the reason that there is a point symmetry is because if you think back, we were able to make an argument that we folded. I know there was a lot of lines, but we folded over a horizontal and vertical line. If you have a horizontal and a vertical line, even though you had all those other lines, if you have a horizontal and vertical line, you can make an argument that there's point symmetry. Okay, and this then would fit into that. So we could add 0, 0. That's the point in the middle. We could add 0, 0 to our list. We just want to be careful that we understand that that is representing the point 0 for r, but 0 for theta. I think that when it says, can we make any conclusions about a rose? Can we make any conclusion about a rose? That I was thinking that you might want to say, as I said a couple times, that it will always go through the petal. So we have this idea of through the petal, but also between the petal. And that is guaranteed to happen every time you have a rose. It'll go through the petal and between the petal. The first rose we did it counted both times. The second rows we did, we had to come up with a new line. So we ended up with double the amount of answers. But you always want to look to see if it goes through and between. All right. It looks like that the remaining 8 problems we can kind of give as some homework. I mean, if you're interested, you could look at a few of them right now, or maybe just find 15 minutes when you're off for the next few days. But I want you to look at some other ones and see if you can identify the symmetry. All right, so don't forget about that, but enjoy having a couple extra days off.